Hello and welcome to this lecture on structural equation modeling. My name is Jörg Henseler, and in the coming minutes I will talk about structural equation modeling and its application. In particular, I will treat composite-based structural equation modeling. Structural equation modeling is a multivariate statistical technique, which means that using structural equation modeling you can analyze several variables simultaneously. It's a technique that is very popular in business and social science. Applications can be found in marketing, strategy, human resources, but also psychology, education research, criminology, and subjects of this type. To a large extent, the scientific enterprise is devoted to understanding the world. According to which mechanism does the world actually work? A quite common technique to better understand the world is to make use of models. Models are simplifications of the world that simply focus on some key aspects. A very well-known kind of model are maps, like the one we see here. A particular type of model are structural equation models. Structural equation models simplify the world by imposing a set of restrictions on the variance-covariance matrix of observed variables. This is a fairly abstract definition. What does it actually mean? Let's say we have some variables, x1, x2 and x3. The variance and covariances of these variables can be expressed in the variance-covariance matrix. It's the matrix displayed below. It's a symmetric matrix. In the main diagonal we have the variances, and in the triangles we have the covariances. Since the matrix is symmetric, the upper triangle is not displayed here. Let's start with building a model. A model consists of variables, relationships between them, and model parameters. Here we have the three variables, and every variable has a variance, sigma 1,1, sigma 2,2, and sigma 3,3. Moreover, the variables covary, and the three covariances are sigma 1,2, sigma 1,3, and sigma 2,3. The parameters of this model can be expressed in the implied variance-covariance matrix as shown below. The model we see here is a so-called saturated model. It is saturated because we have as many parameters as there were non-redundant entries in the original variance-covariance matrix of the three variables. Here we have another model. This model connects the variables by means of causal relationships. For instance, x2 can be expressed as b1 times x1 plus zeta1. This model has 5 parameters. The variance of the exogenous variable, sigma 1,1, the two path coefficients, b1 and b2, and the two variances of the disturbance terms, psi1 and psi2. By means of these 5 parameters, the implied variance-covariance matrix can be constructed as shown below. Here we only make use of 5 parameters to explain the world. As you can see, there is a simplification. Instead of the original 6 values, the variances and covariances between the variables, we only need 5 parameters to express the relationships between the variables. Here we see an example of a structural equation model as specified in the composite structural equation modeling software Adanko. How does the process of model building and theorizing look like, let's say, in marketing? Let's look at an example. Marketing is the science of exchange. The one important question is, what makes people buy? To come up with an explanation for people's purchase behavior, marketing scientists would develop a theory. or a conceptual model. A theory consists of concepts, which are abstract terms to represent phenomena, and the relationships between these concepts. Let's say we want to theorize about purchase behavior. Purchase behavior could be triggered by purchase attitude, and purchase attitude might be influenced by an appealing product presentation. Research usually does not stop with theory building. We also want to test these theories empirically. What does this mean? Well, it means some extra work for the researcher, because the theory is located, one could say, in the plane of theory. It is entirely abstract, and by itself it is not accessible through empirical measurement. What we therefore need is a connection, so-called correspondence rules, with observed variables. These correspondence rules that connect the abstract concepts with observed variables is the domain of auxiliary theory. So in order to test theories, substantial theories, we also need auxiliary theories that tell us how we can measure or how we can build the theoretical concepts of interest. How can we choose an auxiliary theory that suits our needs? When we choose the auxiliary theory, we should think about which types of law govern our phenomenon of interest. Are these laws that are human-made? Then we could think, for instance, of recipes or construction guidelines. And then we have some freedom how to interpret them, and we might deviate a bit from these guidelines. On the other hand, if we have natural law, then the phenomenon will simply occur, and we have not any choice whether we want to obey to the law or not. It will just happen. So if our phenomenon obeys to human law, we would use synthesis theory. It's about building or constructing our concept. Whereas if our phenomenon obeys natural law, then we should think of choosing measurement theory, which is about measuring the phenomenon of interest. If the phenomenon of interest exists without human intervention, then we should think of applying measurement theory. Measurement theory postulates that a concept exists and it is the underlying cause of a block of observed variables. In a statistical model, we would use a latent variable to represent this concept. The axiom of local independence helps to lay the link between the theoretical concept and the observed variables. It reads as follows: a block of observed variables are independent of each other given the latent variable scores. That means if a concept exists as manifested in a latent variable, then the observed variables should exhibit a certain behavior. Namely, they should be independent from each other given the latent variable. Measurement theory is realized by means of so-called reflective measurement models, in which latent variables are modeled as common factors. Measurement theory bridges the gap between the observed variables and the abstract concepts in 3 steps. Firstly, a common factor is extracted from the observed variables. This is then a proxy for our abstract concept. If this common factor explains the common variance of the indicators, that means the axiom of local independence holds, then this common factor is elevated to a latent variable. It means we have sufficient certainty that there is a concept underlying the observed variables. As the final step, we interpret the latent variable in our statistical model as being equal to our concept of interest. Synthesis theory comes into play as an auxiliary theory if we have concepts that can be designed, created, or engineered. Synthesis theory postulates the usefulness of a formed concept that emerges out of more elementary components. In synthesis theory, we don't work with latent variables, but with emergent variables. And an emergent variable represents the formed concepts in the statistical model. The axiom of unity is at the core of synthesis theory. It says a set of components forming an emergent variable acts along a single dimension in accomplishing its purpose. Synthesis theory is realized by means of composite models, in which emergent variables are modeled as linear combinations of other variables. Some people call emergent variables formative constructs. However, I would not recommend using the term formative constructs because it can so easily be confounded with the formative measurement of latent variables, which is something different. Synthesis theory bridges the gap between the observed variables and the forged or formed concepts. Synthesis theory also makes use of 3 steps for this endeavor. Firstly, there is a prescription of how to combine the more elementary components into composites. These composites will then be elevated to an emergent variable if the axiom of unity applies. And these emergent variables are then interpreted as the formed or forged concept of interest. Let's now look a bit more into the technical issues of structural equation modeling. Structural equation modeling can be thought of as consisting of 3 more elementary techniques, namely factor analysis, path analysis, and some form of composite analysis. This is visualized by this methodological family tree. It all goes back to bivariate correlation as a measure of linear relationship between 2 variables. The left branch characterizes psychometric research, in which factor analysis and later confirmatory factor analysis have been developed. The middle branch characterizes the econometric development, where multiple regression analysis was developed and then later path analysis. The right branch is the youngest one. It consists of canonical correlation analysis and lately confirmatory composite analysis as 2 techniques that work with composites. Structural equation modeling integrates these 3 branches, which certainly adds to its complexity. Structural equation modeling consists of 4 steps. The first step is the model specification. The second step is the model identification. The third step is the model estimation. And the fourth and final step is the model assessment. Let's start with the first step, the model specification. A structural equation model can be thought of as consisting of 2 submodels. Firstly, the inner model, which contains the constructs, that means the latent and the emergent variables and their relationships, and the outer model, which connects the constructs with their respective observed variables. The inner model is a representation of the substantial theory, whereas the outer model is a representation of the auxiliary theories. Also, the present model can be split into 2 submodels. The inner model consists of the constructs and the relationships between them. We distinguish between exogenous variables and endogenous variables. Exogenous variables are those variables that are determined entirely by factors outside the inner model. There are no arrows of the inner model pointing on exogenous variables. In contrast, endogenous variables are at least partially explained within the inner model. Therefore, there is always at least one arrow pointing on them. The outer model contains the relationships between the constructs and their respective observed variables. We distinguish between emergent variables and latent variables. Emergent variables are symbolized by a hexagon, whereas latent variables are symbolized by an oval. Please also note that the arrow direction is different. In composite models, the arrows point from the observed variables to the emergent variable. In reflective measurement models, the arrows point from the latent variable to the observed variables. 6 different symbols are usually employed in structural equation models. Squares or rectangles denote indicators or observed variables. Ovals are used for latent variables, or in general unobserved variables. Hexagons represent emergent variables. Please note that emergent variables can be observed or unobserved depending on whether their indicators are observed or unobserved. Circles represent error terms or disturbance terms. Single-headed arrows represent linear relationships, and double-headed bowed arrows represent covariances, or their standardized form, correlations. Specifying the inner model entails selecting the constructs that should form part of the model and specifying the relationships between them. Several kinds of relationships are available. Direct relationships are denoted by single-headed arrows. They symbolize causal relationship. In the current example, we would thus say that eta 2 is hypothesized to be caused by eta 1. Indirect, or so-called mediated relationships, are characterized by the fact that two variables are not connected directly, but via a third variable. In this example, the relationship between eta 1 and eta 3 is mediated by eta 2. So we have a direct effect from eta 1 to eta 2 and from eta 2 to eta 3, but no direct effect from eta 1 to eta 3. Unanalyzed relationships are characterized by the fact that there is some relationship between eta 1 and eta 2, but it is not specified what kind of relationship this is. So there might be a direct relationship between them in either direction, or there could be a third variable influencing both, but there is just no focus on this relationship between eta 1 and eta 2. So we simply let them covary. That also means both eta 1 and eta 2 are exogenous variables in our model. No relationship means exactly this. There is no relationship between two variables. In our case, eta 1 and eta 2. If eta 1 and eta 2 are both exogenous variables, then also the covariance and correlation between eta 1 and eta 2 will be 0. If one or both of them are endogenous, there could be some covariation or correlation between them if there is an indirect effect or a third variable influencing both. Nevertheless, a direct effect between both of them would be 0. A fifth kind of relationship between two variables is a spurious relationship. In this example, the relationship between eta 1 and eta 2 is spurious. If one only looked at these two variables, one would find a correlation or covariance different from 0. However, it's not that there is a direct relationship between the two, but there is a third variable, here eta 3, which causes both of them. That means the relationship between eta 1 and eta 2 is 0 and it's spurious. Once we have specified the inner model, we can continue with specifying the outer model. Actually, specifying the outer model means that for each construct we need to specify an outer model. We need to decide whether as auxiliary theory, synthesis theory, or measurement theory is applied. If synthesis theory is applied because we have a formed or foraged concept, then we would use a composite model in our structural equation model. In contrast, if measurement theory was employed, then we need to look what is the epistemic relation between the indicators and the latent variable. If the indicators cause the latent variable, then we would have a so-called causal formative measurement. If the indicators are consequences of the latent variable, then we would use a reflective measurement model. Actually, the reflective measurement model is a sort of gold standard, and the causal formative measurement model always needs to be accompanied by a reflective measurement model. Therefore, the practical usefulness of causal formative measurement is somewhat limited. The central place in a composite model is the emergent variable, here symbolized as a hexagon. In synthesis theory, a synthesis takes place. The indicators or observed variables make up the emergent variable. They do not cause it, but they make it up. This is important to know, that the error relationship here between the indicators and the emergent variable is a material relationship of making up and not a causal relationship of influencing. Dropping one indicator could change the meaning of the emergent variable. The observed variables can be correlated, and that's why these covariances are drawn in the picture on the right. However, they are not required, so there don't have to be correlations or covariances between the observed variables. They can be zero. The weights W1 to W3 are typically estimated, but they can also be predefined or preset by the researcher based on prior knowledge or expertise. If they're estimated, particularly by means of multiple regression, one should be aware that there could be multicollinearity, particularly if the sign of the weights is counter the analyst's expectations. Multicollinearity is likely to be a problem. This screenshot shows how the composite model looks like in Adanko. In this case, there are two emergent variables, eta1 and eta2, both of which are specified by means of a composite model. At the heart of a reflective measurement model is a latent variable, symbolized by an oval. Measurement is implemented in such a way that variation in the latent variable is inferred from variation in its indicators. The latent variable has causal effects on its indicators. That means the indicators are causal consequences of the latent variable. And because of that, the indicators are expected to be correlated. Dropping an indicator from the measurement model does not alter the meaning of the construct. Measurement error is taken into account at the indicator level. That means every indicator is regarded as a measurement error prone manifestation of the latent variable. This screenshot shows a reflective measurement model specified in Adanko. The measurement errors are not displayed in order to preserve clarity. However, they do form part of the model. They haven't been forgotten. Sometimes researchers would like to include categorical variables into their models, particularly if a variable acts as a control variable. It can very often happen that it is categorical. Think, for instance, of variables like gender, marital status, industry, level of education, and so on. Including categorical variables is quite simple. You can do that by means of specifying an emergent variable and using dummy variables as indicators. Concretely, you should transform your categorical variable into one dummy variable less than you have categories. In this example, we have a categorical variable marital status with 4 categories: unmarried, married, divorcee, and widower. We then construct 3 variables, one called married, one called divorcee, and one called widower, which have a level of 1 if this category is present and a value of 0 otherwise. The reference category is unmarried. That means if all three indicators have a level of 0, then the category unmarried is active. Model identification is the second step of structural equation modeling. It means that structural equation models should be specified in such a way that they only have one solution. Well, you already see that the word specified forms part of the definition, so one could regard model identification as an additional requirement to specification. However, most times in the literature it's regarded as a modeling step on its own. To understand the issue of model identification, let's look at an instance where a model is not identified. On the upper left we find a reflective measurement model with two indicators. This model actually is not identified. The variance-covariance matrix of observed variables is printed at the lower left. The variances of both indicators are 1 and the covariance is minus 0.36, which in this case is the same as the correlation. In the upper right we see several pairs of parameter values that would be valid. For instance, minus 0.6 for lambda 1 and plus 0.6 for lambda 2 would be valid estimates, but also 0.6 for lambda 1 and minus 0.6 for lambda 2, or 0.9 for lambda 1 and minus 0.4 for lambda 2. Actually, most values between minus 1 and 1 for lambda 1 and minus 0.36 divided by this value for lambda 2 would work. So we see that an infinite amount of parameter values imply the same variance-covariance matrix, namely the variance-covariance matrix of observed variables shown below. In order to ensure identification, researchers usually follow sets of identification rules. For the kind of structural equation modeling we are covering, namely composite-based structural equation modeling, there are essentially only two identification rules that play a role. All other aspects of identification are taken care of automatically. These two rules are, firstly, that for each construct the analyst should determine one indicator, the so-called dominant indicator, of which the analyst is sure that it must correlate positively with the construct. Secondly, each construct requires a nomological net. That means it must have at least one non-zero path or covariance with some other construct in a structural equation model. So we see that had we followed the second identification rule, we wouldn't have entered the identification problem that we saw before. Model estimation is the third step of structural equation modeling. Model estimation entails the determination of values for the model parameters. The structural equation modeling literature has suggested several estimation methods. Probably the easiest but also most primitive approach is to simply set parameters. This is, for instance, done in sum scores, where the weights of a composite models are all set to equal values. But one could also set parameters to different values, for instance based on the experience of the researcher. Next to that, one could use real estimation methods, like for instance partial least squares for composite models or consistent PLS, PLSC for reflective measurement models, generalized structured component analysis for composite models, and integrated JESCA for reflective measurement models. Or one could use maximum likelihood, unweighted least squares, or other fitting functions. When choosing an estimation method, researchers must acknowledge that there is no one-size-fits-all option. So they need to consider what is most important for them. Is it the consistency of estimates? Is it the statistical power? The reliance on distributional assumptions? the convergence behavior, the flexibility, or maybe something else? Maximum likelihood, for instance, is asymptotically efficient and excels with respect to flexibility. On the other hand, sometimes it faces convergence problems and it relies on distributional assumptions. PLS is not as efficient as maximum likelihood, not that flexible, but it shows a good convergence behavior and has a decent statistical power. So it is a good compromise. The fourth step of structural equation modeling is model assessment. We can distinguish between two parts. Firstly, the global model assessment, and secondly, the local model assessment. Global model assessment should be performed first. We look at the issue whether the model is a good representation of the world. If it's not, then we should not make use of the model and we should not interpret it, rather we should stop there. Only if the model has an acceptable fit, then we should continue and assess the model locally. We can then check whether we are confident with the measurement or the construction of our latent and emergent variables. And if we are, then we should interpret the relationship between the constructs. The core question of structural equation modeling is whether the model is an adequate reflection of the world. At the heart of structural equation modeling lies the question of model fit. Does the variance-covariance matrix of the observed variables equal the implied variance-covariance matrix? The implied variance-covariance matrix, sigma theta, is that variance-covariance matrix that we would expect if the world functioned according to our model. Theta is the set of all model parameters. That means the lambdas, the psi's, the w's, and the b's. In empirical research, there will virtually always be a discrepancy between the model implied and the empirical variance-covariance matrix. However, the question is whether this discrepancy is systematic because the model is wrong, or whether this discrepancy can be attributed to sampling variation. So we can run a test that tells us whether the discrepancy is significantly different from zero. For this purpose, we need to specify distance functions that quantify the fit or the misfit actually. Here we find two such distance functions. Firstly, the maximum likelihood distance function, dml, and second, the geodesic discrepancy, dg. Both quantify the discrepancy between a model implied and an empirical variance-covariance matrix. They have the characteristic that in case of perfect fit, the discrepancy would be zero, whereas in all other cases, the discrepancy has a positive value different from zero. Once we have chosen a discrepancy function, we can run a sort of simulation study, the so-called Bollen-Stine Bootstrap. The Bollen-Stine Bootstrap works as follows. We define the population as our model, and we draw samples from this population. And for each sample, we estimate the model and we get a discrepancy. Note that the discrepancy that we get is a discrepancy despite the fact that the model is correct. And after having run hundreds of samples, we'll get a distribution of this discrepancy if the model is correct. And then we can determine the 95 and the 99% quantiles of this empirical distribution and use this for inference statistics. Once we have the empirical discrepancy distribution, we can look back what our original discrepancy was and compare it with the quantiles, the high 99 or the high 95. We can find the values and the high 95 and high 99 values in the Adanko output. Adanko provides these model fit figures for the estimated model and the saturated model. The estimated model is the model as specified by the analyst. The saturated model has a modified inner model, namely it allows all constructs to covary. That means there are no constraints in the inner model. For the model below, we could thus say that the saturated model has an excellent fit and the estimated model still has a good fit. Eventually, there are some constraints in the inner model which are too rigid. So it is worth the effort to inspect the model again for potential overlooked relationships between constructs. More often than not, it happens that the model does not have fit. Or, expressing it in terms of inference statistics, the model is significantly wrong. What to do then? Well, following the scientific realist paradigm, one would then have to stop. Say, well, the world functions according to a different mechanism, not to the one that I thought, so let's search again, let's come up with a new theory and test that one. However, that produces quite some research waste. The whole data collection, the study design has caused lots of effort, and maybe there is at least something that we can learn out of it. And what researchers then sometimes do is, instead of checking whether the model fits in an absolute term, they check whether the model fits at least approximately. That means they acknowledge that a model is wrong, but they would like to know whether it's at least close enough so that one can learn something from it and get some ideas about how the mechanism of the world could look like. Actually, one changes then the scientific paradigm. One knows that the model is wrong, but one then asks, is the model then at least still useful? Like a map, which is definitely wrong, it can still help us to guide the way. In the same way, a statistical model which is wrong, but has nevertheless a close fit, might still be a valuable resource for gaining knowledge. Therefore, researchers make then use of measures of approximate fit, and the SRMR being one of its most famous exemplaries. We can compare the model implied with the empirical variance-covariance matrix, or we can compare the model implied with the empirical correlation matrix. That's the case when we look at the SRMR. The SRMR is also a measure of misfit, and it is defined as shown in the formula here. It is typically used as a fit index. That means one does not test whether it's significantly different from zero, but one looks at its absolute value. The recommended threshold is 0.08 and a more rigorous threshold is 0.05. If the discrepancy that one has obtained for one's model falls below these thresholds, one would say that the model at least approximately fits well. Once we find that our model has sufficient fit, we can continue with the local model assessment. Assessing composite models is mainly performed along the model parameters. One would start looking at the composite weights. What is their sign? What is their size? What is their significance? Then one could look at the composite loadings. What is their sign? What is their size? And what is their significance? If the indicators are uncorrelated, then the weights and the loadings would be roughly proportional. However, if they are correlated, then the weights could have quite a different pattern than the loadings. The other way around, if the weights have a very different pattern than the loadings, we can conclude that multicollinearity is playing a role. Assessing reflective measurement models is usually done along certain quality criteria. One would usually start looking at the reliability of the construct scores and use several reliability indices for this endeavor. Then one would look at the indicator reliability. Then one would check the validity, and this would be convergent validity and discriminant validity. The first reliability index is Cronbach's alpha. Arguably, Cronbach's alpha is the most prominent reliability coefficient and also most widely used. It can be determined using the equation shown here. It measures the reliability of a set of equally weighted indicators, so-called sum scores. Typically, it lies between 0 and 1 if all indicators have positive correlation, so one can construct situations in which alpha is negative. In real research situations, you will obtain negative alpha if you forgot to recode a reverse-coded item. In early phases of research, a value of 0.7 is regarded as acceptable. In later phases, the threshold should be higher, for instance 0.8 or 0.9, according to Nunelli in 1978. Inferential statistics on alpha exist, but they are not widely used, probably because they are not implemented in SPSS. Alpha has the characteristic that it increases with the number of indicators. Some people find this a disturbing behavior, but on the other hand, it makes sense because a test with only a few items has much more random measurement in it than a test with many more items. So it makes sense that alpha becomes larger the higher the number of indicators. Finally, Cronbach's alpha assumes a tau equivalent measurement model, which means that all indicators have the same amount of useful variance. This assumption is quite rigid. That means in real-life research situations, Cronbach's alpha will most likely underestimate the reliability. Jurys-Cook's rho is another reliability coefficient that overcomes some of the disadvantages of Cronbach's alpha. Other names for Jurys-Cook's rho are composite reliability, factor reliability, or McDonald's omega. Like Cronbach's alpha, also Jurys-Cook's rho measures the reliability of a set of equally weighted indicators. This reliability coefficient definitely lies between 0 and 1. The thresholds in interpretation are like Cronbach's alpha. Jurys-Cook's rho is applicable to congeneric measurement models. That means the indicators may have a different amount of useful variance. Whereas Cronbach's alpha and Jurys-Cook's rho quantify the reliability of sum scores, rho A measures the reliability of a composite as created by PLS. If the model is well specified, rho A will lie between 0 and 1. The thresholds and interpretation are the same as Cronbach's alpha, and it's applicable to congeneric measurement models. The indicator reliability quantifies the amount of variance in a reflective indicator that is explained by the respective latent variable. It can be interpreted as an R-square. Therefore, it lies between 0 and 1. If the indicator and the latent variable are standardized, the indicator reliability equals the squared indicator loading. Convergent validity can be established by means of the average variance extracted. The average variance extracted is a sort of average indicator reliability. it lies between 0 and 1, and it should be higher than 0.5 according to Fornell and Larker, 1981. The last part of measurement model evaluation refers to discriminant validity. Discriminant validity can be assessed by means of the heterotrait-monotrait ratio of correlations, or in short, HTMT. The HTMT departs from the logic that the correlations between the indicators belonging to the same construct should be higher than those correlations between indicators that belong to different constructs. So we have the ratio of monotrait heteromethod correlations and heterotrait heteromethod correlations, out of which the HTMT is made. Constructs that are conceptually different should also be statistically different. Therefore, the correlation between constructs should be smaller than 1. The HTMT is actually an estimate of the correlation between latent variables. In order to ensure that the correlation between latent variables is smaller than 1, we can either refer to criteria, such as a threshold of 0.85 or 0.9, or we can rely on inference statistics, so we can test whether the HTMT is significantly smaller than 1. Once we deem the outer model appropriate, we can continue with assessing the inner model. Starting point for the assessment of the inner model is typically the coefficient of determination of the endogenous constructs. The coefficient of determination, also called R², quantifies the amount of explained variance in an endogenous construct. It's also sometimes called fit in the econometric literature. The R² is known to be increased by an increase of independent variables, and it gets smaller the more observations one has. Therefore, an adjusted R² has been introduced that accounts for sample size and the number of independent variables. Particularly if one wants to compare models, then the adjusted R² is more useful than the plain R². Let me come back to the concept of fit. It happens, unfortunately, that the term fit is used twice in the statistical literature, but for two different things. This has to do with the fact that it was developed in the econometric literature and in the psychometric literature. In the econometric literature, the term fit is sometimes used synonymously for the R², whereas the psychometric use of fit is the one that we have taught in this course. It's the discrepancy between the model implied and the empirical variance-covariance matrix of observed variables. One can construct situations where the two meanings of fit diverge. One such situation is the current one, where we have two variables that are hypothesized to be unrelated. So that's what the theory says. The first variable has nothing to do with the second variable. If we run a correlation analysis or regression analysis, we would obtain an R² of 0. So there is no econometric fit. However, if we model our theory with structural equation modeling, then we would get the empirical result that the two variables are unrelated, which is exactly what the theory is about. So we would get a perfect fit. The empirical variance-covariance matrix would be identical with the model-implied variance-covariance matrix. So perfect fit. So we see that we might have situations where we have no econometric fit, but perfect psychometric fit. And it shows how important it is to distinguish between the two concepts that both carry the same name, namely fit. Many analysts regard the path coefficients as the most important output of structural equation modeling. The path coefficients are the parameters for the direct effects. They can be interpreted like regression coefficients. That means an increase in the dependent variable if the independent variable is increased by 1 unit and all other independent variables are kept constant, so-called ceteris paribus. Particularly the second half of this sentence is very often forgotten in practice, but it's very important to correctly interpret a direct effect. Path coefficients can be inspected for their size, their sign, and their significance, as expressed whether they are significantly different from 0, or we can look at their confidence intervals. Analysts interpreting path coefficients must take into account that the path coefficients might be affected by multicollinearity, and they must be aware that path coefficients tend to become smaller the more independent variables a dependent variable has. In order to overcome these problems with path coefficients, Cohen proposed the so-called effect size, f². f² is calculated for each effect. It is calculated as the difference of an r² of a dependent variable where the effect of interest is included, minus the r² of a dependent variable when the effect has been excluded, divided by 1 minus r² included. A nice feature of the f² is that there are some common thresholds that can be used for interpretation. If the f² is higher than 0.35, one can speak of a strong effect. If the f² is smaller than 0.35 but higher than 0.15, one can speak of a moderate effect. If the f² is smaller than 0.15 but still higher than 0.02, one can speak of a weak effect. Finally, it might also be that we have a significant effect whose effect size is smaller than 0.02. In such a case, one would speak of an effect that is hardly substantial. Finally, there are 3 other categories of output for the inner model. Interconstruct correlations are particularly interesting for the relationship between exogenous variables. The indirect effects are useful to quantify the mediation effects. Total effects are interesting for success factor research. PLS, JESCA, and many other composite-based structural equation modeling estimators do not make distributional assumptions. This is nice when it comes to requirements for the data, because you can apply these methods to skewed data, to kurtotic data without many problems. However, it fires back when it comes to inference statistics. You cannot rely on parametric assumptions if you didn't make them before with regard to the data. Fortunately, there's a solution to this problem. We can rely on non-parametric inference statistics, and in particular, the Bootstrap. The Bootstrap can be used to estimate measures associated with estimated parameters, such as standard errors, if no closed form formula exists. The Bootstrap assumes that the collected data is representative for the population one wants to generalize to. In inferential statistics, we make an inference from a known sample to an unknown population. We are well aware that a sampling error occurs, but we cannot quantify it directly. We usually make some parametric assumptions, and by means of that, we can quantify how large the sampling error is. However, if we don't want to make these parametric assumptions, we need to go a D-way. And the Bootstrap is such a D-way. The idea behind the Bootstrap is that we can simulate the sampling error that happens if we draw a sample of a certain sample size. And we simulate this sampling error by drawing bootstrap samples from the sample. And the sampling error occurring in this process is equal to the sampling error that we have between the sample and the population. In the context of structural equation modeling, the bootstrap is performed as follows. Firstly, a high number of bootstrap samples is drawn from the original sample. Let's say, for instance, 4,999 bootstrap samples. Then, for each bootstrap sample, the structural equation model is estimated. In that way, one gets empirical bootstrap standard deviations, and these standard deviations can be interpreted as standard errors of the parameters. This is possible for the path coefficients, the indicator weights, and the indicator loadings. In addition, one can also construct percentile confidence intervals. Once we have the bootstrap standard errors, we can conduct significance tests just like in the traditional way. So if we want to test whether population parameter beta is different from 0, we create a test statistic, a t-value, where we divide the sample estimate b and divide it by the standard error as obtained from bootstrapping. This test statistic can then be compared with the critical values of the t-distribution, and then we can see whether the coefficient is statistically different from 0 or not. Alternatively, one can assess whether the bootstrap confidence interval contains the value 0. With this, we've come to the end of today's lecture. I would like to thank you for your attention, and I wish you lots of success with your statistical analysis using structural equation modeling.